efforts. This is, I would say, fundamental physics in action. As we all know, Alain Aspect, John Clausier, and Anton Zeilinger, they were awarded 2022 Nobel Prize in physics for their experiments, on entangled photons and establishing the violation of Bell inequalities. This is what I'm going to talk about is exploitation, of basically Bell inequalities and its application in actual communication systems to achieve physical layer security. Okay, this is going to be an overview of my talk. This is a longer summary, but I think I'll be able to complete this part of it. Quantum key distribution is an important application of quantum technologies, entanglement and superposition properties of photons. So I'm going to overview the standards, network layers related to quantum key distribution. And then quantum random number generators are also an important part of physical layer security and quantum key distribution protocols. That's also based on quantum properties of particles. This is the part that I'm going to talk about. The next part would include quantum information theory highlights and analysis, correctness and security of these protocols would complete the entire picture, but that I think we don't have enough time to cover all of these topics. Quantum secure communications is really an interdisciplinary subject. It covers a broad range of sciences, including information science, physics, engineering applications, Shannon information theory, as well as quantum information theory, complexity theory, and many other fields. So it's at the intersection, of all these different scientific areas. The secure communications that is based on the principles of quantum mechanics. It's one of the mature and commercialized applications of quantum technologies. There are many other applications of quantum mechanics, quantum computation, and others that we have been discussing in this conference and other places. But this is, I would say, the most mature and it's already been commercialized application of quantum technologies. And the security in this kind of an application is it's inherent, it's ensured by the basic laws of physics and also postulates of quantum physics. In quantum secure communications, two of the major postulates, usually of quantum physics are exploited. This is the superposition principle and quantum entanglement. Superposition principle is basically leads to the uncertainty in measurement in non-orthogonal basis. This is in the literature referred to as prepare and measure techniques, because you are preparing a particle, let's say in this case a photon, in a certain state, and then you are making a measurement. So these, if you want to classify, these communication techniques, first one would be prepare and measure, that would be based on the superposition principle, and second one would exploit the entanglement property of particles. So entanglement, as we all know, it's a non-classical statistical correlation, basically, in the properties of two or more quantum particles. These properties could be their spin states of electrons, or maybe polarization states of photons, or ground and excited states of atoms. This is what actually Einstein had referred to spooky action at a distance, in the famous EPR paper in 1935, that seemingly two particles, no matter how far they are, would affect, once you make an observation on one of the particles, the particle A, it would make an instantaneous effect on the state of the second particle, no matter how far they are. So this is the property that we'll be exploiting in secure communications. Just to give you more information or more explanation on the superposition principle, this is on the right-hand side, we see the block sphere. Any qubit, basically, that we could represent as ket psi equals alpha ket 0 plus beta ket 1, where alpha and beta are complex amplitudes. Could be represented on this block sphere as a point, on this block sphere. So both quantum computation and also quantum communication consist of manipulating this qubit using operations, gates on this qubit and moving this basically this qubit on the block sphere. That's the whole idea behind quantum computation and quantum communication. So a qubit, in this sense, is a superposition state of these computational bases, what we call computational bases ket 0 and ket 1. So when a measurement is made on this particular qubit, the technical term is collapsing. The state of the qubit collapses to one of the basis states, either ket 0 or ket 1. So it would collapse to the ket 0 state with probability alpha magnitude square. Since alpha is a complex number, so magnitude square of this value would be the probability of measuring ket 0 state, and likewise magnitude square beta would be the probability of measuring the ket 1 state. So this ket psi is called the wave function. It reflects the state of the qubit, and in theory, any information on the quantum state can be obtained from this wave function. So it's a very basic, property or basic entity in quantum mechanics. So information is encoded in this state of these superposition states of qubits. So based on how we position this qubit in the block sphere, for instance, if we want to encode the one state, we could position on the z direction, positive z direction, on the block sphere. And that qubit would represent basically one state. And if you'd like to encode 0, for instance, information, the minus direction, -1 direction of in the z vertical direction would represent the ket 1 state of this particular qubit. Okay. So these qubits, encoded with particular state, encoded with particular information, can be used in symmetric key encryption. Symmetric key encryption is, let's suppose we call Alice and Bob. Alice is the transmitting party and Bob is the receiving party. Let's suppose Alice has a plain text that she would like to encode or encrypt using a cipher, using a key. And Bob, likewise, in the scheme of symmetric key encryption, would typically have the same exact key as Alice says, and would decrypt the ciphertext. But the problem over here is the secure distribution of the key. Let's suppose there is another party, Charlie, preparing these keys that would distribute these keys to Alice and Bob. The problem is how you would distribute these keys to Alice and Bob, making sure that there's no eavesdropper on this particular key, because key is the most important component, of symmetric key encryption. Once the eavesdropper, or what we call Eve, has an access to the key, then she can, easily decrypt the message. So this is the general scheme. And as we mentioned, this key can be generated and distributed through what we call quantum key distribution protocol. And there are actually networks of this because in a networked scheme, for instance, you don't have only two parties. It's not usually a point-to-point communications. It is a networked in a networked environment. You'd like all of the parties, participating in this communication would share, the same key. So these key distribution protocol is usually implemented in a networked situation. And quantum random number generators also is an important part, as we are going to see, of these QKD protocols. It's again the general scheme of communication between Alice and Bob. Alice as a plain text, and then there's an encryption algorithm. And according to this encryption algorithm, Alice encodes the information on a quantum state. And then this qubit, particular qubit encoded with this information is transmitted through a quantum channel to Bob. Quantum channel could be an optical fiber, or in certain applications could be free space. But we also need to implement securely these protocols, a public channel, a classical channel. Classical channel could be internet or telephone network. As we'll see, almost in all cases, one would need both of these channels. Public channel that is accessible by anyone, including Eve, and also a quantum channel, similarly, that's also accessible to Alice, Bob, and Eve, outside intruders. Okay. Just like conventional communications networks, these are also quantum-based key distribution networks, also have layers very similar to the OSI layer classification or TCP/IP layer classification. We have a physical layer, data link control layer, network transport, and application layers. And the actual quantum key distribution algorithm is implemented typically in the physical layer. So that was the reason why we call this physical layer security. Physical layer is the actual medium, where the information is transmitted. The quantum key distribution and quantum communications is so much, well advanced that nowadays even standards organization, including International Telecommunications Union, ITU, ETSI, IEEE, they have their own working groups to develop standards, how to implement these, because there are already quite few products in the market, and we would like to make sure these products are all secure and safe, and also they are compatible at the same time with each other. So all these organizations, and as Bilgem also from TUBITAK, we are participating in these standards organizations, and we try to contribute, to these standards that will, I think, be finalized, in the very near future. So in this standards protocol, this box, where we call quantum layer, includes all the functions, of generating keys, encoding qubits, and this general, diagram also depicts, how this box, quantum layer communications box, is interfaced, with the other layers of the protocol. So this is a typical QKD system, components of the QKD system. As we mentioned, there is a sending unit, transmitting unit, which we called Alice, and also there is a receiving unit, which we called Bob. There is a signal source. Signal source is basically the information. It represents the information that would be transmitted to Bob. And the modulator is where this signal source is encoded, on the quantum particle, in this case, photon. And then all of these protocols, basically, they include a random number generator as well, and control electronics, to control the modulator, the signal source, and a random number generator. On the receiving side, again, this information, some of this information is classical bits that is transmitted through a classical channel, and also the qubits, are transmitted through a quantum channel. On the receiving end, we have a signal demodulator, again a random number generator as part of the protocol, control electronics, and detectors. So this is as depicted by the European ETSI, European Telecommunications Standards Institute. This is a general framework for a QKD system. Now let's look at some applications, some details. Like in this particular application, the previous diagram was a generic depiction. But in this particular example, we use, again, we have these random number generators, control electronics, but now we the random number generator dictates the phase of this is a Mach-Zehnder interferometer that's used to encode the state of the photon, and for the phase modulators basically and together with the Mach-Zehnder interferometer make sure that the state that we'd like to transmit is encoded on the phase, in this case, of the photon. And similarly, in the receiver side, we have a Mach-Zehnder interferometer now to demodulate the received state of the qubit. This is another example of a QKD system and its components. Now it's based on, the previous one was based on prepare and measure technique, where we prepare state of a particular photon. In this case, the state encoded being the phase, of the photon. Now this is another example that uses an entanglement-based QKD system. As we see over here now, in this case, we have an entanglement source. It generates two photons that are entangled. And these photons are transmitted through a quantum channel, which is a fiber, in this case. And related electronics, including Bell inequality measurement circuits and detectors are also involved, because you need to make sure that when the entangled pair of photons are generated, there's no interception, and that interception is detected through Bell state analysis. We have again avalanche photodiodes, to receive and detect single photons, and FPGAs for implementing the actual protocol. So this is an example of an entanglement-based QKD system. As we said, in terms of the network architecture, the quantum layer in all these protocols, the generation of qubits, encoding the qubits, random number generation. We are going to see other post-processing, which we'll call key distillation. All of these are implemented in the quantum layer. So a typical QKD protocol, both including prepare and measure technique and also entangled photon technique, it includes two parts. One is the generation and transmission of the qubits that represent the Rove key. We call this Rove key because that's not the actual key that Alice and Bob would use eventually. These keys would be sifted, in other words, using classical post-processing. Only part of these keys, Alice and Bob would use. So it would include a Rove key generation and qubit transmission part. And also, it would the second part of the protocol would include always a classical post-processing, where we ensure Alice and Bob has the actual security, safe key that they would use in encryption and decryption. So that's called the symmetric crypto key. As we said, there are two kinds, major kinds of quantum key distribution protocols. One would use prepare and measure approach that would exploit the superposition property. In this case, Alice would encode a string of classical random bits in a non-orthogonal or orthogonal quantum states of photons. Like non-orthogonal meaning she could pick, for instance, the eigenvectors of X and Z Pauli operators that they would represent non-orthogonal basis. And then Bob would receive these qubits and performs measurements to produce the raw key. The typical example of this is the BB84 protocol that was invented by Benet and Brassard and AT&T Bell Labs, at the time. And as the name indicates, this was invented in 1984. So this shows how far, back the use of quantum technologies go back to in the application in communications. And the second would be entanglement. Again, raw key data transmission is through the entanglement property of the qubits. And this would entail basically generating the entangled photon pairs and then using Bell state measurements to ensure that there is no interruption, or there's no intervention in the communication. Usually in practice, instead of the Bell state measurements, people would use more equivalent to Bell state measurements, but other protocols that are easier to implement. One of them is the CHSH protocol. The name John Clausier, you see over here, is one of the Nobel laureates. I mentioned, in the beginning of the talk. He was the person, actually, when he was in the US, the first person who demonstrated non-local, non-classical correlations in two qubits that are situated, far apart. So this whole story actually started with John Clausier, and then continued with Bell and others, John Bell and others. So typically, one would use this CHSH protocol to verify the non-interception, of the qubits by an eavesdropper during the transmission. This is called E91. Arthur Eckert in 1991 was the first person. He's now in the UK, who has shown that entanglement could be used for secure data communications. So after his name, this protocol is referred to as E91. Here's a list of major QKD protocols that have been introduced, since 1984. As I mentioned, all of these protocols, they are based on two types of approaches. They are variations on these approaches. One was the prepare and measure approach. We said would exploit the superposition principle of a qubit, and the second would be the entanglement approach. So in each iteration, of these protocols, some safety features, of the protocol is improved. So this is like a short, maybe a set of, short example, list of examples of such QKD applications. The Heisenberg uncertainty principle over here basically refers to the prepare and measure, because if you measure in non-orthogonal basis, there is an uncertainty, in the measurement. That's why it's called over here Heisenberg's uncertainty principle. So after the key is generated through an entanglement or other means, and we obtain the raw key, there is classical post-processing. What does this classical post-processing do? It involves several stages typically, and it makes sure that the key that Alice and Bob has, they are the same actual key, and also they are distributed in a secure manner. One is the key sifting, the first stage. That's the reduction, basically, of the raw key, where parts of the key is eliminated. That Alice and Bob, think that Eve has access to. This is called key sifting. And part of the keys are also, part of the raw key is also used for channel parameter estimation, a quantum bit error rate, basically. The error rate, there's also noise, in the communication channel. And also there are, of course, measurement and other errors. So for in real applications, one would need to estimate the communication channel parameters. And also there are error correction also. This is classical error correction. In a typical communication system, it's possible to add redundant bits. You have your actual data bit stream, but then you can add a set of redundant bits. So in case of an error in the real data, one could use the redundant bits to correct, the possible errors that could occur in the actual data stream. And there is also a fourth element, which we call privacy amplification. This is an information theoretical approach where we eliminate the information that is obtained by Eve on the key. So these 4 steps constitute classical post-processing part. In a typical, for instance, BB84 QKD protocol, which is based on prepare and measure, Alice now is the transmitter, Bob again is the QKD receiver. There is a set of generated raw bits, raw classical bits that are encoded on the qubits and transmitted to Bob. And then these qubits, these raw data is encoded on the qubits through the use of some basis. In this case, for instance, we use Alice uses either rectilinear basis or diagonal basis. Rectilinear basis is the basically eigenvectors of the Z Pauli operator. Diagonal basis is the eigenvectors of the X operator, and at random encodes these bits. And then there is the sifting stage where Alice and Bob, they announce, both the basis, of encoding basis and measurement basis that they have used. If the encoding basis and the measurement basis they match, they select those bits. If they don't match, they discard. Again, there's some loss. In each stage there is loss of the actual raw keys that have been generated. And then there's the key distillation phase, where the channel parameter is estimated, there's error correction is done, and the privacy amplification. The 4 stages, post-processing stages are implemented. So eventually, out of a long string of raw keys, Alice and Bob now has, as a result of this protocol, a shared secure key. This is how BB84 protocol would work. There are a few ways, of classifying QKD protocols. I'm just looking. How am I doing with the time? Okay. There is a first classification. Okay. Okay. There's, as we said, the classification we mentioned, preparation and measurement, or entanglement encoding classification. Another classification one could look into is device-independent or device-dependent protocols. Device-independent protocols would mean even the Eve would know the particular transmitter or receiver structure, the particular receiver and transmitter structure, and the protocol is known by Eve. Still, the protocol works securely. These are referred to as device-independent protocols. Another way to look at these protocols is one-way or two-way, bidirectional or single-directional qubit transmission. And the fourth way that we have not seen so far, but I'm going to do some explanation on this also. Discrete variable or continuous variable qubit encoding and decoding. In discrete variable QKD systems, one would use single photons. The information is encoded on the properties of a single photon. And also this would require, of course, single photon generation and single photon detection, equipment hardware. But in the case of continuous variable, as we'll see, the one would use a laser, a classical laser beam rather than a single photon. And the information is encoded on the, because a laser beam is basically an electromagnetic wave. So it has quadrature components, and the information is encoded on the quadrature components of the laser beam. The continuous variable, the advantage of continuous variable QKD is it's possible to use already available equipment that one would use in optical communications, fiber optics communications. It's basically the same equipment one would use. So it's in practice, this continuous variable systems are getting more and more popular. So discrete variable QKD, as I mentioned, one would use a single photon, and the information is encoded. There are discrete states or discrete data that one would like to transmit, and the information is encoded in the quantum states of a photon. The quantum state could be the polarization, the orbital angular momentum, as we have seen, the phase, any property of the photon could constitute the state, of a photon where we could encode this information. And the encoded photons, then they are received by Bob. They are, in this case, received by a single photon detectors. These are avalanche photodiodes, could be popularly used, or nowadays the photo detectors, based on superconductivity. They are much more sensitive, close to 100%, 98% quantum efficiency is possible nowadays with these superconducting detectors. It's based on the photon. When the photon is hits, on the surface of a superconducting surface, the heat that's generated by the photon, basically it changes the resistivity. So by using, the resistivity, changing resistivity values, one could detect, a photon. That's the most efficient way of single photon detection. And there are, again, quite few well-known examples. They're all based on, as I said, either prepare and measurement or entanglement, but these are the varieties of different kinds of discrete valued QKD systems. In the case of continuous valued QKD, one would, as we said, encode the information to be transmitted on the quadrature components. We call X1 and X2 components of the electromagnetic field of the photons or the laser. These are X1 quadrature components. These are the components in the optical phase space. And when Bob receives this laser beam encoded on, and the information on the encoded photons, he uses coherent or coherent homodyne or heterodyne detection. These are techniques used in optical communications, so equipment is readily available, to do these measurements. Okay. When it comes to the security of QKD protocols, how secure are these protocols? There are two basic approaches to this. One, there is the information theoretical security. It's always possible to compute the mutual information that Eve would obtain by measuring the qubit using quantum information theory, or even in certain cases classical information theory. But in the real applications, the level of security is usually is less than this. That's because there could be certain loopholes, in the, as we are going to see, in the hardware, in the device, in the software implementation. The implementation is usually never, as exact, as defined in the actual protocol. And this is called implementation security. In implementation, because of the loopholes, there are always, unsecure means, that Eve would use to intercept this communication. I'll show these things in a separate slide, so I'm going to skip these for the sake of time. So this is a list of security attacks that Eve can implement on the communications channel. The security attack could be either to the photon source, photon detection, or encoder and decoder of the communication system. It's all, for the purpose of gain information on the key. So all these attacks, would be possible. I'm not going to go into the details of this, but there are. This is a quite, involved research field to understand, security features and, compute and analyze security characteristics of QKD systems. Are the QKD protocols, are there any implementations of this? Yeah, yes, there are. There are many test beds worldwide, actually, in Europe, in Japan, and the most recent one is the Chinese MICU satellite system, where a low Earth orbit satellite transmits an entangled pair of photons to two stations on Earth, two locations, and then going through the bell state analysis and other security checks, one could distribute entangled pairs and consequently a secure key to two parties. So the objectives of all these Chinese and Singapore experiment and other test beds is to have a secure network worldwide, a global network where you could ensure secure communications from any point A to point B. That's the whole purpose, and that's guaranteed, by the laws of physics. Yeah, I'm not going to go to the details, but these are all variations, of the BB84 of the different DV-QKD, discrete value QKD protocols. Like, for instance, in B92 version of the BB84 protocol, instead of 4, non-orthogonal bases, this is a version of it where it would be possible to use 2 non-orthogonal bases. Or in the case of the 6-state protocol, as we remember, the block sphere that we have seen, at the beginning of the talk, it has 6 antipodal locations. So it's possible to use all these 6 states, instead of 4 states to transmit information at a higher rate. And there are other versions, like SARC-04 that's implemented in the Tokyo quantum key distribution network that would eliminate attacks, based on photon number splitting, PNS attacks, so there are all versions of this particular protocol. Okay. This example, which we call coherent one-way protocol, was actually the reason I'm showing this is this was implemented at TUBITAK on an optical table using standard optical components. In 2014, it uses the source now is attenuated, laser source, so that you make sure, the photons are coming, individually, are transmitted individually. So it encodes the information on the time bins, transmitted. So 0 and 1 bits are encoded in this way. Again, you have a quantum channel and a classical channel. Okay. So as you said, in the continuous variable quantum key distribution, as opposed to discrete variable quantum key distribution, one would use lasers instead of single photons. Lasers and also homodyne and heterodyne detectors. And the information is encoded on the quadrature components of the laser beam. And this is a typical implementation of such a protocol. There's a laser source and encoding and quantum channel is in this case a fiber channel and the homodyne detector. The commercialization studies of continuous wave and QKD and discrete valued QKD, there are quite few commercial products nowadays, and even some of the commercial organizations, like the banks, there are the implementations for some time are there. Banks and other places, besides this testbeds, other government organizations use QKD protocols. There are suitable commercialized products, both in continuous valued QKD and also discrete valued QKD. I would like to say a few statements on quantum random number generators, because this is together with QKD, quantum random number generators also exploit quantum properties of photons, typically photons, but it could we could use other quantum systems besides photons, but in this case photons. The number random generators can be classified as pseudo-random number generators. These are basically, they depend on deterministic algorithms. They appear random. I mean, if you look at the autocorrelation function, they appear random, but they are deterministic. They typically use shift register sequence and other deterministic algorithms. So if one would have access, if Eve would have access to the particular algorithm, it would be possible for her to produce the exact random number sequence in this case. There are also true random number generators. These are still classical. They don't use any quantum property, such as the terminal noise on a resistor, atmospheric noise. One could sample all these noise sources and come up with random numbers with a random number generator. But as opposed to all of these, quantum random number generators are the randomness is generated by the laws of physics. Like, for instance, if you toss a coin, head or tail, apparently it's a random number source, but it is due to the lack of our detailed information on the actual physical system. If one would know the details of all the position and also momentum, of the initial conditions of the coin, in principle, it would be possible to compute, whether you would deterministically whether you would obtain head or tail. But in the case of quantum random number generators, the randomness is due to the laws of physics. You don't have any means actually computing the actual number. It's not based on the insufficient information that one would have. Rather, it's because of how physics work. And one example of this could be, let me give some examples. For instance, the decay time of an isotope, the beta decay. This time is a random source, and the randomness is guaranteed by quantum physics. And similarly, beam splitters, a photon hitting a beam splitter, whether it will be reflected or transmitted, that's also related to quantum physics. That's also a real random number source. Just like the QKD, a random number source, even if it is a quantum random number source, we need to do a post-processing. For true randomness, the source should be uniformly distributed and statistically unpredictable. In other words, future data, past data should not have any information on the future data. It shouldn't be possible to have any information or compute the future data based on past data. So to ensure this statistical characteristic, one would make sure the data is uniformly distributed and statistically unpredictable, uncorrelated. So this would require post-processing. This diagram basically summarizes what I just said. Okay. So skip this. Okay. So I think I've taken much longer, than I should have. But if this would have been a real, like a coursework or class, or longer, if you had a longer time, then would describe maybe some quantum information theory highlights, some minimum information on how information is defined in quantum systems, and how quantum channels, would have, because just like classical communications in quantum systems, also the source, has carry, some information. The channel, has quantum information theoretical capacity. So for full understanding and analysis, of such systems, one would have to know some quantum information theory. And also, we could, using these tools, we could analyze all these protocols, and we just talked about, BB84, E94, and analyze and do apply CHSH tests and best state analysis. Okay, and also just before closing, I'd like to mention teleportation. I didn't mention much over here. It's also an important component of quantum networking and quantum communications, because of the non-cloning theorem. In a typical classical communication system, one could easily store and amplify, the stream, of bits, you would like to transmit. But in the case of quantum communications, because of the no-cloning theorem, it's not possible to copy a qubit and retransmit. So one uses, and there are also now physical implementations of this to teleport. And this protocol is called entanglement swapping. One could use entanglement swapping even on a chip. You could like one part of the chip to transmit a qubit. All these things are implemented, and they are possible. And another important maybe aspect of this would be implementation of all these protocols using linear optical elements. Like lenses, mirrors, polarizing beam splitters, delay elements. These are all linear optical elements. Apart from a few particular cases, it would be possible to implement all these. There are, in details, you would need some nonlinear optics and some electronics, but in general, most of these protocols, it would be possible to use linear optical elements, to implement either on desktop or on a chip. All these things are possible. Okay, so thank you for listening. Sorry for keeping you, longer than planned, but
we would like to thanks for your good talk. Any comments or questions? Yes, Şemsettin Hocam.
If the Eve is listening all the time, and how would you transfer the key from Alice to Bob?
okay. So, like in the case of, for instance, entanglement-based protocols, E91, a CAD protocol, using statistical analysis, of the qubits received, Alice and Bob, basically implementing, belt state analysis, they could infer, whether there has been an eavesdropping or not. Like in CHSH test, for instance, they do some correlation measurements. If it is below 2, that particular correlation, then they say, there has been a measurement by Eve, so this, entanglement has been destroyed. But if it is 2 times square root of 2, there is an equation that I have not described over here. So if the correlation, is above 2 and below 2 square root of 2, then Alice and Bob, would infer, there has been a non-classical correlation, quantum correlation. So there's no, eavesdropping on the transmitted qubits. So it's basically using belt state analysis.
You're using the belt state analysis, but if the Eve is continuously without interrupting, is the listening?
Yeah. Then they retransmit, basically.
Yeah, it's listening all the time. Yeah, he tapped onto the communication lines or receiver, whatever it is, and continuously is the listening.
Yeah. Well, I mean, then they would retransmit until until they make sure, that
Until they make sure.
Yeah, there's no interruption.
I see.
I mean, in the technical analysis, it's easier to describe, how this could be implemented in practice, but roughly, this is.
But also Alice will not know whether or not the information is compromised by only the Bob will know. So Bob has to communicate with Alice.
No, Alice and Bob, they share, this kind of information. The statistical analysis results they share until they both, make sure that they have, they have the right, secure key. So both Alice and Bob, as a result of this protocol, they make sure the key is secure. Yeah.
Each time Alice will generate another key, each time it will send different keys, and those keys on the way will be listened by the key. If third party sets up another system on the path and keeps listening all the time, then how would you transfer the key from one to the other one? That's the problem.
Yeah, but I mean, I would say it's not possible to always intercept, because let's say you are doing this on a satellite transmission. You have the entanglement photons, just like in the Chinese case, the Miku satellite. They are prepared in the satellite and they are transmitted to the ground. So it's not always possible to capture, each one of the photons, right? Entangled photons that's transmitted to the ground.
But also that they encoded the information for the non-entangled photons, because most of the photons, there's a probability, are lost on the way.
Yeah, especially in the atmosphere, 1 in a million, typically, once you send the entangled pair, because of the interaction, with the atmosphere, the molecules in the atmosphere, the coherence, is destroyed.
Of course.
So, but 1 in a million, like these things have been measured of the photon pairs. they reach, you know, the ground without losing the entanglement. And they use coincidence detection, you know, just to make sure, you know, because they need to identify the pairs, you know, of entangled photons. They cannot just, you know, pick, you know, random photons. So they use coincidence detection, and they implement CHSH, you know, tests on these particular entangled photons.
The problem in the communication, since they are encoding the information into a bunch of photons, some of them is arriving to the detector over there. Some of them is arriving to somewhere else. For example, some of them are lost in the atmosphere, of course.
So they just pick the ones, you know, that have, because all of these entangled pairs, right? They are basically like one of the Bell states.
Yeah, you're right.
You can use one of the Bell states. So at the time of measurement, Alice and Bob, you know, depending on what Bell state they use, is transmitted. Either they have the same random bit, or you know, opposite random bits. Yeah.
Any more questions or comments? Thank you, Orkun Hoca.
Okay. Okay. So sorry for keeping you, you know, so long. Okay. Okay. Thank you very much. Thank you very much.